Good day, everyone. Our group will be presenting the development of an adaptive cruise control system on an electric golf cart. This project demonstrates the full control system design process where we model the vehicle behavior, design the controller, and validate the performance through simulation. We will explain the motivation, the modeling approach, the control structure, and the result that we obtain. These are the members involved in this project. Each member contributed to different components such as modeling, simulation, controller design, analysis, and report development. Our combined work allowed us to complete both the system design and the final evaluation of the adaptive cruise control system. Let us start with introduction. As mentioned earlier, our group worked on the development of an adaptive cruise control system for an electric unmanned ground vehicle, which is electric golf cart. These vehicles are commonly used in convoys or in industrial tasks where automatic distance keeping is important for safety and efficiency. The aim of this project is to create a complete control workflow starting from modeling and simulation, followed by stability analysis, controller design and validation with a lead vehicle profile. Moving on to the workflow of our project, our work starts with the longitudinal modeling of the vehicle. This includes the motor behavior, drivetrain, traction force, and all resistive forces such as rolling resistance, aerodynamic drag, and any gradient load. After building this subsystem in Simulink, we examine how the vehicle behaves under a simple throttle command. This open-loop study helps us to understand the natural behavior of the system before adding a controller. After completing the modeling, we proceed with linearization to understand how the system behaves near a specific operating speed. This prepares the groundwork for the adaptive cruise control structure, which uses both a speed loop and a distance loop. At the end of the project, we validate the complete controller using a simulated lead vehicle profile. I will now pass to the next presenter who will explain the modeling and open loop findings.
Assalamualaikum and hi, my name is Daniel and I'm going to present on the vehicle modeling and also the open loop system. Our modeling begins with a force balance in the longitudinal direction. The traction force from the motor must overcome the resistance force. This relationship determines the acceleration and also the speed of the vehicle. The motor torque is produced based on the total command and is limited by the rated torque and also power. The drivetrain passes this torque to the wheels which generates the forward force. The distance model is created by integrating the difference between the speed of the lead vehicle and also the speed of the ego vehicle. This gives us a real-time estimate of the spacing that will later be used in the controller. To check whether the model behaves correctly, we apply a step throttle input. The results show a small increase in speed toward a steady value. The motor torque begins at a high level and reduces as speed increases. This is consistent with the behavior of a real electric motor. The resistance force follows the expected trend and rises as the speed becomes higher. The open loop response behaves realistically and does not show any instability. This confirms that the model is suitable for further analysis. Next, we look at the stability of our system around the operating point. I will now hand over this presentation to the next presenter who will cover the linearization and also the controller design.
To understand the local behavior of the system, we perform a linearization at a chosen steady speed using MATLAB code. The result gives us a transfer function that represents the behavior of the motor torque in response to a throttle input. The poles from this transfer function lie in the stable region, which means the system is naturally stable. However, the response is relatively slow, which is common for a vehicle that carries significant mass. With the linear behavior understood, we designed the adaptive cruise control structure. The controller uses two feedback loops. The inner loop regulates speed by comparing the actual speed of the vehicle with the target speed. The outer loop regulates distance by comparing the actual spacing with the safe spacing. The safe spacing depends on a static distance and the time headway multiplied by the current speed. If the ego vehicle is too close to the lead vehicle, the distance error becomes negative and the controller will reduce the speed. If the ego vehicle is further than the safe distance, the controller allows it to accelerate. The controller gains are tuned throughout repeated simulation to ensure smooth behavior and effective tracking without oscillation. The complete Simulink structure links the motor model, vehicle dynamics, distance model, and both feedback loops. I will now pass to the final presenter who will describe how the controller performs in the final validation.
To evaluate our adaptive cruise control system, we simulate a scenario where the lead vehicle follows a predefined speed profile. The ego vehicle starts from rest and adjusts its speed to match the lead vehicle while keeping a safe spacing. The speed tracking showed that the ego vehicle reaches the target speed smoothly with only a very small overshoot and an almost zero steady state error. The acceleration and jerk remain within comfortable limits, and the distance tracking shows that the ego vehicle does not violate the required safe spacing, although the spacing reaches the boundary value at one point. This is expected because the ego vehicle starts from rest, while the lead vehicle is already moving. Now, according to the performance criteria, the system meets the requirements for safe distance, stable behavior, and steady state accuracy. Some metrics, such as the initial tracking error and the settling time, appear to fall outside the target range, but these results come from extreme starting condition. Once the vehicle is moving, the controller performs well. So, in conclusion, the project demonstrates the complete workflow of a control system design process. We created a realistic model, analyzed its behavior, designed a two-loop adaptive cruise control structure, and validated it with simulation. The system is able to follow the lead vehicle smoothly and maintain safety throughout the test. Thank you.